scientists pursue their dream using advanced camera systems, the space shuttle, and satellites far above Earth. Stunning images lead them to discoveries beyond what can be seen.
Different effects produced by the same forces which create the visible northern lights. For science, the search has been to find their cause. When standing beneath such an enormous presence as the Northern Lights, people of the North in every century have tried to depict the spectacle with whatever image they could from their earthbound, ground-level view of it. Aurora, as it's known today, was believed to have been named in the 17th century by scientist-philosopher Pierre Gassendi, and theories began. But not even Ben Franklin's theory described the aurora's source as any higher than the clouds. It was a while, too, before the Earth's magnetic field was accepted widely. Careful record-keeping built up data about the range of the auroral occurrences. 19th century explorers seeking a northwest passage through to the Canadian Arctic contributed to Earth's familiarity with the forms of the aurora. One of the earliest debates about the aurora scientists engaged in was the determination of the aurora's height. It is not possible to estimate the height without a reference. Carl Stormer successfully applied a triangulation method using stars as a reference. Since the 17th century, it was known one could determine height by finding the distance between two viewpoints and the angles of sight. It wasn't until the invention of the camera that the process could be exact. The technologies of the camera, accurate clock, and the telephone made it possible for researchers to coordinate their photographing precisely. Technology has extended the perceptions of scientists and explorers. Today's technologies are allowing us to voyage farther into the auroral environment. Using such technologies, science not only gains new images of auroras, but also new approaches to investigation. Researchers can go physically closer to the aurora, where they can study it experimentally, and then move scientifically closer to solving century-old mysteries. Often the analogies which scientists use to develop theories for solving the mysteries can make understanding the aurora easier for us. Shunaka Sofu, auroral physicist, explains the aurora as an electrical discharge in a vacuum.
The aurora is an electrical discharge phenomenon. An easiest example is a neon sign. If you want to make a neon sign, you have a thin glass tube, vacuum the air, and then put a little bit of neon gas in, put electrodes, and then connect this one to a high voltage supply. If you do that, then electrons run from the cathode to the anode.
When they run through this tube, they collide with the neon gas. the neon gas atoms are hit by the electrons, become energized, and as they go back to the lower state, they emit light.
This is the only light that the neon can produce. No other atoms can produce this particular light.
In the upper atmosphere, where auroral displays occur, there is also a vacuum. Here, molecules of nitrogen emit a reddish color, and atoms of oxygen emit whitish green. Like a neon sign, the aurora's lights also have a high-voltage supply.
There is an invisible generator in the sky.
A generator has a conductor, such as a coil, running through a magnetic field.
It so happened that the Earth is a gigantic magnet. The Earth has a dipolar magnetic field. Those loops are called magnetic field lines. Instead of a coil, we have the solar wind. The solar wind is a very hot, 1,000,000-degree gas blowing out from the sun with a supersonic speed. Because it's so hot, it consists of only charged particles. This gas of charged particles is called a plasma. The solar wind blows toward the Earth, then confines the Earth's magnetic field into a cavity. It is on the boundary of this cavity that the generator is working, supplying the power for the auroral electrical discharge.
When we see auroras from the ground, they change in a number of ways. The more activity, the larger becomes the scale of the folds. From the ground, the aurora will appear different depending on our viewpoint. The aurora is 1,000 miles long, 60 miles up, and several hundred miles high. Often it's our perspective that changes the appearance. The whole aurora looks like a folded cloth curtain. If we are looking at a fold from directly underneath, there's an optical effect of lines converging within that fold, called a corona. When the aurora is viewed from some distance, more of its shape appears. When it is viewed from spacecraft, the whole shape becomes clear. Finally, the global changes during the aurora are more visible from a higher altitude satellite viewpoint. These are phases of activity in a surge of energy, or substorm. Thus, the lights change in appearance several ways, depending on which phase the aurora is in, where it is viewed geographically, and how intense is the activity. Scientists use the space shuttle to study the changes in the appearance of the aurora occurring because of space and time. Spacelab gave University of Alaska Fairbanks physicist Thomas Hallinan and co-investigator astronaut Don Lind a viewpoint away from the Earth, from which they could observe the whole aurora across the globe.
SRB ignition, and Challenger in Spacelab 3 is airborne and has cleared the tower.
Tower clear. Houston now controlling. Roll program initiated. Roger, roll, Challenger. Seconds, roll program completed.
The space shuttle was really the first time that we've had any sort of high-resolution data from space, or high-resolution visual data. We're seeing images in rapid succession, can see how the aurora moves, how it changes with time, also how the appearance of it changes with perspective as the spacecraft moves past it. This is something that simply has never been done before.
From spacecraft, much more of the aurora is visible to study. When the shuttle's highly sensitive black and white television camera recorded the aurora, it was in the right place at the right time.
It turned out that we did get a very good view of the southern aurora, and this really is roughly equivalent. It really didn't make much difference to us whether we saw the southern or the northern aurora because they're the same. This is something that we had a chance to check ourselves a number of years ago. We flew 2 aircraft, one out of Christchurch, New Zealand, flying towards Antarctica, and another out of Anchorage, Alaska, flying towards the Arctic coast of Alaska. And then we looked at the aurora in the 2 hemispheres, and it was the same. It was pretty close to a mirror image in the 2 hemispheres.
The southern aurora they observed was more intense than anyone anticipated.
This is the aurora, the northern, or in this case, the southern lights. This is really one of the spectacular views of a natural occurrence on Earth. To see the whole sky illuminated below us against the moonlit clouds was really spectacular. This goes from horizon to horizon. The atmosphere is bombarded with electrons coming in from the magnetosphere, and currents surging through the ionosphere cause the air particles to glow.
You'd need a film with an ASA rating of around 1 million to get movies of the aurora. So this is basically what we were after. We wanted movies of the aurora. You can't do it with film. Turns out you can do it with television, not a standard television camera like people use for home video. But recently, a color camera has been developed that is actually sensitive enough to record the aurora and produces studio quality pictures. There are 2 of these cameras. They're built in Japan. One of them we have now. That's our first chance to really record it and then start looking in detail about how the colors relate to each other. What this is, when you look at the aurora on a sideways view, you see these what appear to be vertical rays, very narrow rays that can dance around and move quickly from one place to another. Well, if you can look at those from underneath, get the cross-section view, then they turn out to be vortex forms, and very much like the eddies along a riverbank. The discovery of those vortex forms made us realize that there were very strong electric fields in the region above the aurora, and this was very highly controversial for a long while. We used the computer to analyze the video pictures. There's so much detailed information in the picture. The challenge is to extract that information, and the computer allows us to get access to it.
Scientists use color stills taken from the shuttle to study the physics and chemistry of the aurora's heated gases, its plasma.
To see this in full color was really spectacular. Plasma instabilities in the plasma caused the motion. Bob took 35 millimeter pictures to document the color because the various color tells us the particular particle that's emitting light.
The study of the colors of light, spectrometry, provides an important indication for physicists of the kinds of atoms and molecules and the temperatures they observe. They have been able to learn about the upper atmosphere and above, where they could not experiment directly, such as on the surface of the sun. When early physicists studied the aurora's colors, they tried to explain them based on the solar spectrum, the visible light refracted in a rainbow or water drops. Some of them thought ice crystals in the polar regions caused the aurora's light. Later, they discovered the auroral spectrum was not continuous like the solar spectrum, but discrete, like the colors in the neon tube. In the tube, each atom emits a different color depending on what kind of gas it is. Mercury, xenon, helium, argon, neon, nitrogen. The aurora's discrete colors come from atmospheric gases, oxygen, hydrogen, and nitrogen. In the aurora, though, the different colors are produced by conditions in the atmosphere as well as by different atoms and molecules. Scientists can learn from studying auroral light what atoms, composition, temperature, and processes are affecting it in the atmosphere. In addition to observing natural atmospheric conditions, Scientists perform active experiments to study auroras. They launch small rockets, sounding rockets, to experiment directly in the aurora. One kind of sounding rocket experiment releases visible elements into the auroral environment. Since the color and characteristics of barium ions, the charged particles, are known, they make ideal tracers when they are exploded from rockets. They can be tracked from the ground in darkness with cameras, image intensifier equipment, or photometers. Gene Westcott uses barium releases to study conditions along the Earth's magnetic field lines.
Well, we send up a rocket with a high explosive shape charge device, which accelerates barium ions, heavy barium ions, up the fuel line. So they followed the fuel line like beads on a wire. We use barium because it's one of the few elements that has visible emissions, and so it's like tossing dye into a stream. You can actually see it if you're in the darkness on the ground. Once the barium is traveling along the fuel lines, it's extremely sensitive to electric fields that are the main interest in where the aurora particles come from. These are like very heavy auroral particles. And so when they're in the presence of an electric field, they'll either drift faster or slower up the fuel line, and they'll go across fuel lines. And by noting this, we can see where the electric fields are that might be causing the auroral features that we're interested in. First we see the initial explosion, and there's the expansion of the explosive gases and barium. And then the ions, the barium ions, are the blue streak coming out. And you'll see the ions coming out as a pencil beam and gradually expanding. And they're traveling at escape velocity so that they will go on up the fuel line, completely traverse the fuel line way out into the magnetosphere, maybe 30,000 kilometers, and come back down to the other end. But if you do another kind of experiment where you put in a lot of energy perpendicular to the field, you essentially twang the field, like you have a stretched wire and you pull it and twang it. Then the barium perturbs the field and you start waves going. It's equivalent to our tossing a rock into the magnetosphere. And it causes the field lines to shake and particles to move and waves to go out, and then we observe the effects that we cause.
Other sounding rocket experiments are the best means of obtaining certain data directly from the aurora, since it's in the no man's land of the upper atmosphere that's too high for balloons and too low for satellites. Poker Flat Research Range near Fairbanks has been providing facilities and arranging crews for sounding rocket experiments by auroral scientists from all over the country. The auroral display occurs more frequently here in the interior of Alaska than at the North Pole. Poker Flat is the only rocket range operated by a university, yet it has some of the most scientific instrumentation associated with any rocket range in the world, and in this unlikely site.
One of the truly unique things about Poker Flat is that it's totally dedicated to the science of the project.
And one of the problems in the last flight was the fact that the aurora moved on us a little bit when we got to altitude. So the intensity of the aurora was not as strong as what we had wanted for our customer.
Spirit 1, the rocket they will launch tonight, is designed to take infrared readings in the atmosphere, positioning highly sensitive instruments at the aurora.
The purpose of the experiment is to measure the energy or radiance that comes from the atmosphere throughout the infrared region. And what we try to do is to fly rockets against these very bright disturbances that we call aurora to be able to determine how the atmosphere changes.
On the 7th, then, we continue cooling, and then possibly on the evening of the 7th, then we will cool the detector.
Right.
And that's the crucial time when we do all of the instrument tests.
Okay.
You say the fin was all the way up to there?
So we have on all the channels. That gives us
The sounding rocket is the only tool that we have to place an experimental package inside of the Aurora Borealis. Every single instrument that's ever been placed aboard a satellite for long-term measurements above the Earth's atmosphere was first developed and flown aboard a sounding rocket. And that continues to be the case today. To do a rocket-borne experiment, you have three pieces of information as a function of time. Number one is, what does the aurora look like from the ground? And that's what the aurora is happening and time goes by. The second is the rocket payload. As it's flying through space, you have to know where it is as a function of time. So we do that with a radar. So we track it with a radar. Again, a piece of data comes out of where the rocket is a function of time. And of course, the third and most important part is, as the rocket flies, it sends the information back on what it is observing in place or in situ, in the sky, on a radio transmitter to the ground. At approximately 4 hours before the attempt to launch, that is, we're down at 5 minutes in holding, everyone meets at Poker Flat. The scientists, the engineers, the technicians, the full crews, the radar crews, the telemetry crews, and everyone. At approximately 3 hours before the launch, the first activity takes place. And that is to use the radar at Poker Flat to track what we call a wind-weighting balloon, which is a small helium-filled balloon carrying a piece of tinfoil. We must know the wind speed and direction from the surface of the Earth to approximately 100,000 feet very accurately. Concurrent with that, the payload engineers in the blockhouse, in what we call the user room, are operating the instruments that are physically connected through umbilical cables from the blockhouse, approximately 500 feet, out to the rocket, the launcher, which has the rocket motor system and payload on board, and the umbilical, of course, plugged into the nose carrying the payload.
Take it off, please.
Also during this time, Pat Young sits in the blockhouse, and of course from the very start, she is announcing over the countdown speakers the status of the count. Scientist, of course, at the same time, is located usually well away from the blockhouse in a quieter area where he can observe the sky, or he can have information fed to him about what is happening in the sky with the aurora. At about 10 minutes in the count, we go through a pretty extensive check.
Station status checks on channel 2, please. Radar.
Go.
TM.
Go.
Wind weight.
Go.
Payload.
Go.
Project scientist.
Go.
Fort Yukon TRADAT.
Go.
Ranges go. All stations are go.
At T-minus 5 minutes on most programs is what we call a hold function. When you get to that point, we define we ask, okay, do we go ahead from here or do we stop? Once the scientist says, let's go, we've got the conditions, I want to launch, we have to do a quick check with the FAA.
We have clearance from the FAA. On my mark, we will be at T-minus 2 minutes.
Once we get the clearance from them, we're off and running. The count proceeds down. At approximately 2 minutes before liftoff, the radar systems are brought through some final checkouts with their internal computers. So as the firing lines are verified, the help of those to make sure that the circuits between the blockhouse and the rocket payload in the last 2 minutes, that everything in there is just really what it ought to be. At 1 minute and on down, everything's automatic and running, and it's just a matter of trying to keep up with it.
Mark, T-minus 1 minute and counting. $30 seconds.
Got lock and load, everything was supposed to be.
20. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, launch. 1, 2, 3, 4, 5.
This is a TV camera on board, which is tied to a TV display and a joystick on the ground. And I use that system to relocate or reorient the payload and the instrument to point at the Aurora.
For over 25 years, sounding rocket experiments worldwide have been contributing to knowledge of the upper atmosphere. In this way, scientists not only use advanced technologies to study the Aurora, but also apply what they can learn from the Aurora to understand space. The Aurora continues to be the inspiration for theories and additional research. First, its location, then explanation, shape, and chemistry, and finally, the mysterious source of its power, the workings of the magnetosphere power generator. To develop approaches to questions about the power supply, some physicists explore the dynamics, the mechanisms causing the Aurora's substorms. How does the magnetosphere supply the additional power to produce the substorm's brightening and increase of auroral activity? How is the solar wind's energy converted to send particle beams streaming toward the Earth's atmosphere? Satellites have been providing data from above Earth and farther away than the moon, out in the magnetosphere, the magnetotail of Earth. Each satellite contributes different data to scientists' knowledge of these plasmas, in the Aurora and in the magnetosphere generator. The Dynamics Explorer satellite now is the only spacecraft far enough from Earth to show the whole auroral oval. Every 12 minutes, it takes ultraviolet and visible light pictures.
The object then with the Dynamics Explorer was to build a camera to look down on the Earth and take a continuous sequence of images. The earlier spacecraft, imaging spacecraft, would develop a picture of the Aurora as they moved across the auroral oval. And you gained the second dimension in building your picture by the motion of the spacecraft. That means it would take you about 12 minutes to cross the auroral oval. You get one picture in 12 minutes, but then you didn't get the second picture of that that hemisphere until the spacecraft had gone completely around the Earth and come back again. So that means it's an hour to an hour and 20 minutes before you get the second picture. Now, the difficulty there is that a typical auroral substorm will last an hour or 2 hours. So you get a picture at the beginning and you get a picture at the end, or you may get no auroral substorm at all. Dynamics Explorer, in contrast, can almost as though it's hovering above the auroral oval. So you can capture the entire dynamic sequence of a substorm for the first time on a global scale. That's really a significant contribution that Dynamics Explorer provided, was the time sequence of a single event from a single observer.
Using their Dynamic Explorer images, Lou Frank is able to determine significant features of the magnetosphere.
Well, when we when we look at the images of the Earth's aurora, the global ones that we've recently obtained from Dynamics Explorer, we can, for the first time, look at the aurora, sort of real time, and look at its entire extent. And from that, we can deduce certain things about what's happening at distances much beyond our own atmosphere. how much energy is stored in the magnetotail by the size of the auroral oval. As it expands and gets bigger, as the auroral oval gets bigger, it means more and more energy is being pumped into the tail, the magnetotail of our planet. And as it's released, it means less and less energy is stored back there. All right. During this contraction and the contraction of the magnetotail and the loss of energy, this energy is pumped into streams of particles that we see on the ground as the auroral substrate. And what is responsible for that release of energy is the great debate of how auroras are stimulated. In particular, the substorms are the great increases of light intensities at a given instant. One of the things that is helpful for us is the following, is that the Earth's magnetic field acts like little wires, all right? So we have sort of a map in a way. So if you were to explore, you know where the aurora was actually created. You can image it, like with D, these fantastic global images. You find a bright spot, all right? Now, if we could take that bright spot and follow and look for the field lines that thread it, and we walked out into the magnetotail along that field line, that magnetic field line, which just behaves like that copper wire, somewhere out there, if I took a journey long enough, I'd come to the power supply. And that's what we're searching for. That's what has yet to be ever reported.
Using IC3 satellite data from out in the magnetotail, Edward Hohn's Los Alamos National Lab is tackling this question of the power supply. He is willing to present a detailed model of how he believes plasma in the magnetosphere behaves during a substorm.
To understand the Earth and the solar wind, one must understand the process of magnetic reconnection.
Plasma in the magnetosphere can be like two magnets. When two bodies of plasma, magnetized in opposite directions, are pressed together, like magnets, their magnetic fields will change direction and align to each other's opposite poles, north to south, so their magnetic field lines appear to reconnect to each other.
Because of enhanced reconnection at the front of the magnetosphere, magnetic reconnection increases, more energy is poured into the magnetotail in the form of magnetic field lines, and this squeezes down the plasma sheet. It causes it to sort of neck down. And the result of this is that oppositely directed field lines in the north and south part of the plasma sheet are pushed closer and closer together until, zap, all of a sudden, the oppositely directed field lines meet and reconnect across the current sheet. And very suddenly, and this happens, and it causes a very rapid injection of plasma toward the Earth, and this results in the brightening of the auroras in the night side of the auroral oval. But at the same time, this reconnection is also causing a cutting off of the plasma sheet. The plasma is jetting tailward, and the field lines tailward of the reconnection region are forming closed loops, closed circles. And eventually the last closed field line of the plasma sheet is severed, and it's no longer connected to Earth. There's nothing to keep it there, and it starts flowing tailward. And it's a large body of plasma on closed magnetic loops, and we call that a plasmoid. It carries something like a half of the energy that's previously stored in the tail. We had formulated these ideas from measurements made with satellites quite near the Earth, 100,000 kilometers from Earth. The IMP satellites and IC-1 and 2. Then an opportunity came along in 1983 to put the IC-3 satellite far down the tail, 1.5 million kilometers down the tail. And this was done, and one of the first things we discovered in the IC-3 data was the passage of huge plasmoids occurring some half an hour after substorms.
There are other theories. So often in science, many could be partially right. It is complicated in the magnetosphere. different scientists may be viewing portions of the whole to draw their conclusions. Besides seeking to understand the cause of the auroras, scientists want to predict storms. There are dangerous effects from the energy released during auroral disturbances. In the Earth-Sun system, the aurora gets its supply of energy from the magnetosphere. The magnetosphere depends on the solar wind, which receives its energy from the sun, especially following solar flares. This sequential transfer of energy can be used to make predictions of auroras. IC3 was an outrider sentry for the incoming solar wind, providing reliable data helpful in making short-term predictions, a half-hour lead before an auroral storm. Poker Flat used these predictions before launches. For longer predictions, magnetospheric and solar physicists traditionally study activity on the sun, sunspots, and solar flares to anticipate geomagnetic storms. At NOAA's Space Environmental Services Center in Boulder, their observatory is part of a worldwide network providing solar activity data to those concerned with auroral predictions. The Air Force sponsors space weather experiments because of their need to plan operations, warning or avoiding the impact of disturbances in the auroral environment. The center makes continuous observations using GOES, the geostationary weather satellite, which also points instrumentation at the sun. In addition, ground-based optical observatories worldwide watch the locations of activities on the sun for the kind of effect it would have on Earth. One of the problems is that not all of the solar flares cause intense geomagnetic storms or auroral displays. Some do, others don't. Shun Akasofu is one of the scientists who was challenged by this difficult problem and has improved predictions of auroras.
The location of solar flare is important. When the solar flare takes place near the center of the disk of the sun, then the gas comes straight and directly hits the magnetosphere. On the other hand, if a flare takes place near the rim of the disk of the sun, then the gas from that particular flare goes about 90 degrees away from us, so we don't get very much effect of it.
He charts the positions of the sun and Earth, determining when the solar flares line up with Earth. He also predicts the intensity of geomagnetic storms.
We're now looking down on the solar system from above. Those spiral pattern you see is the solar wind magnetic field. In order to predict the intensity of geomagnetic storm, we have to predict the power of the generator after solar flare. The power of the generator depends on the speed of the solar wind and intensity of the solar wind magnetic field and the direction of the magnetic field.
Akasofu's scheme on prediction will be fed into the Department of Defense main computer system to predict the times and locations of auroras for their data. The aurora is just the visible part of a large-scale electrical discharge phenomenon. Invisible, changing electric fields caused by the auroral discharge cause many other phenomena. An electric current of up to 1 million amperes flows along an aurora in the ionosphere. This current causes geomagnetic disturbances in high latitudes, and when currents vary, magnetic field changes induce electric currents in long conductors on Earth, such as long pipelines, power lines, and telegraph wires. The Trans-Alaska Pipeline, covering hundreds of miles in the auroral zone, physicists predict could have a greater risk of corrosion because of this increased ion migration. The pipeline company, Alyeska, however, checks the pipe carefully and uses coatings for protection from other sources of corrosion anyway. While they were checking the pipeline, they have found the instrumentation which measures the corrosion was unusable during magnetic storms. Power companies are regular subscribers to auroral warnings from NOAA. The longer the line, the larger the voltage the aurora induces. associated current in the telegraph line during the intense aurora of 1897 was so strong that for 2 hours they sent messages between Boston and Portland, Maine, without a battery. Even modern lines can experience blackouts due to auroral storms. The currents surge intermittently through protective relay devices in the line and cause them to trip off, stopping that line's power transmission. The power lines have to be long enough to conduct currents. If there is such a problem during an auroral storm, the company can shut down the lines and reroute to others.
Oh, man.
There's ongoing interest in the possibility of biological effects from magnetic field changes. Some species of birds use the Earth's magnetic field to aid their navigation. Pigeon racers get sunspot forecasts because they fear they will lose birds during magnetic storms. When auroral events affect communications in circumpolar regions where transportation is also often unreliable, its impact is even more dramatic than for our technology-dependent cities. Emergency high-frequency radio is used to link the central, larger village's doctors with the outlying village's local health aides.
Okay, it sounds more like a hive, sir. COVID and itching.
Hives, I think, because they're real big patches,
However, during an auroral disturbance, changes in the ionosphere disrupt this frequency's radio signal. The challenge to meet this vital communication need for Alaska bush villages' health led to an advanced satellite telecommunications system that is a model to the developing world. Scientists and engineers helped the state to improve communications with a higher frequency satellite system. The health aides could relay symptoms to doctors and receive replies on treatments and decisions on whether to call in air rescue or take the patient to the doctor for examination. Ever since this development in the 1970s, Alaskan villages have been connected to each other and to the rest of the world by satellite for television, radio, and telephone.
He's got a lot of...
Laverne and Shirley at 7:30.
Happy days, Laverne and Shirley.
Soon I see the little, you know, the, like, breathe. I shut me, just pass to that wall, pass to, like this.
Within this auroral zone surrounding the Arctic, geography, terrain, and climate already strain many technical systems for communications, radar, and transportation. It is in these same geographic extremes, where there are highly charged ionized particles from the aurora, that national defense systems have to operate.
Elmendorf Airways, Foggy 66 on 5656 upper.
Froggy 66, Froggy 66, this is Elmendorf, sir. Be advised I have you weak readable. How copy Elmendorf?
Elmendorf Airways, come in. Elmendorf Airways, Foggy 66, unable this transmission.
Some long-distance over-the-horizon radar uses frequencies, UHF, that irregularities in the ionosphere make unreliable. Radar for the detection of transpolar aircraft flights sometimes observes signals which could disguise approaching aircraft. In an auroral environment, high-tech surveillance systems are threatened. Radar detection, thermal detection of exhaust plumes of aircraft and missiles in an auroral background become very complicated. Designers need to account for the aurora. Through knowledge of the aurora's wavelengths and the ability to predict them, these problems are manageable. Low-altitude communication satellites of interest to telecommunications as well as to the military suffer increased drag in the heated upper atmosphere of the aurora and can be degraded to the wrong orbit or burn up in the atmosphere. An orbital change would make them ineffective for the military. The problem has more impact because satellites are supposed to compensate for loss of communications on HF. NASA, earlier in the space program, underestimated such auroral effects on their satellites. After several missions, the plan was to boost the Skylab vehicle into a permanent work location to maintain it for 10 years. The sunspot cycle was 3 times more intense than they expected. A space shuttle mission planned to rescue it was not ready in time to push it out into orbit. The vehicle experienced a higher drag than expected from the heating in the atmosphere, re-entered the atmosphere, and plunged into the ocean near Australia. Astronauts, too, are exposed to dangerous high-energy particles from the sun and auroral electrons from the magnetosphere. The space shuttle offers plenty of shielding for working inside. However, during EVAs, extravehicular activities, there is a radiation hazard. X-rays generated by the auroral electrons eventually will penetrate the spacesuits and could cause sterility or death. The spacesuits are enough protection for current missions, activities, and orbits. In the future, though, with longer EVAs, transpolar orbits, and missions at distances where there's greater particle precipitation, the risk from radiation increases. As scientists experiment more in the radiation belts, they will try to improve conditions so that it will be less dangerous for work outside space vehicles. Increasing the world's knowledge of the aurora and related effects is preparation for the future, to extend exploration in many areas of science, in space and on Earth. Robert Hellawell's team is preparing for the future using high-powered radio transmitters to study the radiation belts and the mechanisms which cause auroral disturbances. They are also recording the man-made and natural sound coming from these invisible particles in space. Their experiments could go into space on the shuttle.
What we are hearing are natural electromagnetic signals coming out of the magnetosphere, which have been created by lightning discharges or by radio transmitters or by natural radiation from the plasma itself. And what is most remarkable is that the Earth's plasma can create intense radio waves of very coherent nature that sound like birds waking up in the morning, which gives rise to the term dawn chorus, and which is really the reason I think that we're all working on this particular subject. There is a source of electromagnetic energy, and that energy storage mechanism is the Van Allen radiation belts. The particles that create the radiation are acting collectively, just as they do in a laboratory oscillator to create a very large signal. What's exciting is that this process is present throughout the cosmos, as far as we can tell, and I suppose it's everywhere that you have a plasma. The transmitter on the shuttle is, in an oversimplified way, intended to extend the experiments that are currently being performed from the ground.
Manned space shuttle flights in transpolar orbits open up numerous opportunities for aurora-related and magnetosphere research. The shuttle could fly through both the northern and southern auroras with each pass. Using the spacecraft to conduct such experiments as barium releases would add an interesting dimension. Tracers released farther away from the Earth by satellites could provide data to solve the mystery of the magnetosphere's power supply. In studying the aurora, scientists have an accessible laboratory to space. The auroral zone is more like the rest of the universe than is anything on Earth. What we tend to think of as our universe, Earth's rich atmosphere, the states of matter here, solids, liquids, and gases, The sunlight we can see that is the right warmth for the systems which depend on it is really the exception in this universe. Space isn't a void, empty. It's filled with plasma, various gases that are in the fourth state of matter. They are so hot that they remain an unstable mixture of positively and negatively charged particles. 99% of the matter in the universe is in this state. We find such a plasma in the auroral zone. The more we learn about the aurora's plasma, the more we learn about the universe. Plasma is the Earth's ultimate energy source, the heat of the stars, thermonuclear fusion, the power we would never run out of. Los Alamos National Lab and others are conducting magnetically confined fusion research, thermonuclear power experiments. To generate power, scientists have to reproduce and contain heat equal to the sun's. For this experiment, they heat and compress plasma in a vacuum tube to 10 million degrees, accelerate it, and then trap it into a containment vessel for study. These experiments have many similarities to the Earth's magnetosphere power generator, but in a smaller form with more compressed plasma.
As in the magnetosphere, magnetic reconnection of the field lines occurs in this device and is extremely important in providing the good containment of our heated plasmoids. Another similarity between these laboratory and space plasmoids is their ability to be launched and propagated over relatively long distances.
Perhaps the most important region is in the understanding of plasmas, the basic laws of plasma. How does matter in the plasma form behave? The Very Large Array radio telescope in New Mexico was a real breakthrough. It provided very detailed observations, high-resolution observations of radio galaxies. And one of the remarkable features of these radio galaxies are what they call galactic jets, jets of plasma coming, streaming many thousands of light years in both directions from the centers of these galaxies. They're very suggestive of closed loop structures, plasmoids, just like we see in the magnetotail of the Earth.
The Aurora provides exceptional conditions in which deep space comes to meet Earth. Those who study the Aurora can study plasma in its natural state, directly measure it, and then infer about distant conditions. What we learn about plasma is applied to understanding other galaxies, stars, nebulae, and quasars. Even study of our solar system requires this knowledge. The other planets have magnetic fields, and some have auroras. In order for the aurora to appear on a planet, a magnetic field, the solar wind, and an atmosphere are needed. Venus has the atmosphere, but not enough magnetic field. Mercury has enough magnetic field, though not enough atmosphere. Saturn and Jupiter and Earth have enough of both. If an extraterrestrial were to come to our solar system, he would notice these three planets over the others because of the strength of their radio waves generated by auroral processes, the energy released by the magnetic field and the solar wind. The Pioneer and Voyager missions observed Jupiter's magnetosphere. It's 10 times that of Earth. It's so large, Voyager could record its auroral effects in the daylight. Io, its moon, is part of it as the conductor for Jupiter's light. If we could see it, Jupiter's magnetosphere would look as big as the sun. Auroras are an indicator of many physical conditions about the planets. The engineering of a space station, the U.S.'s Space Race Challenge, also requires knowledge of the plasma environment. A station is out in the intense electron heat and hot plasmas of the magnetosphere. Since people will be spending more time there, depending more on complex technical systems for support, they will need to understand it better. In studying the aurora, scientists are developing knowledge about our next environment, the the rest of the universe.
Competition is forcing us forward to try and solve the problem of what the underlying physics is. If we understand that physics, you can go forward. And even astrophysics, you can go to the large galactic systems, the very energetic systems, which are just plasmas on a huge scale, almost incomprehensible in dimensions to what we work with and live with on Earth, and try and understand them.
The first satellites carried instruments to learn about the auroras. So the study of the auroras has led to a great intellectual adventure for mankind, and is continuing.
Production of this program was made possible in part by grants from the Alaska Council on Science and Technology, the Corporation for Public Broadcasting through the Pacific Mountain Network Program Fund, and the University of Alaska Foundation.